Hi everybody, and welcome to a little lesson on something called improper integrals. The integrals we've studied thus far have represented signed areas of bounded regions. However, areas of unbounded regions also arise in applications and are represented by something called improper integrals, and that's what we're going to talk about today. You can see that there's a blank in our objective. I want you to kind of fill in that blank as we move on with that. So there's two ways an integral can be improper. The first way is that the interval of an integration may be infinite, and the second way is the integrand may tend to infinity. So we will first deal with improper integrals over infinite intervals, but one or both endpoints may be infinite. So you can look here where the left endpoint is from negative infinity to some value a of the interval. The second one here is from a to some value a to infinity, and the last one is from negative infinity to infinity, so both endpoints are infinity. And you may ask, how is this an infinite area going to have a finite, or an infinite unbounded region going to have a finite area? Well, we'll talk about that as we move on. So I want you to first look at this integral and look at it and say, okay, here we have e to the negative x, and we're going to evaluate it from 0 to infinity. So anyone think about how we're going to do this, filling in the blanks? Let's see. Well, we can take the integral of e to the negative x. Anyone know what that is? You should know what it is. Ooh, I'm going to use black here. So it's negative e to the negative x. And we're going to go from 0 to infinity. Well, we're not going to be able to just plug in infinity in for x. We're going to have to actually do something with it. We're really going to have to do something with it. Anyone think of what that could be? That fill in the blank? Well, actually what we're going to be doing is we're going to actually rewrite this guy to begin with. And we're going to write it as the limit as r goes to infinity of the interval 0 to r of e to the negative x dx. So then when I take the actual integral of it, this is no longer infinity. How we're going to write this down here is the limit as r goes to infinity of 0 to r here. Alright, so watch how we evaluate it. Take the limit as r approaches infinity. We're going to substitute first fundamental theorem of calculus right here. So negative e to the negative r, putting that in there, minus the negative e to the 0. Now if we evaluate this limit as r approaches infinity, what is this going to approach? If you said 0, you would be correct, because remember, this is like writing 1 over e to the r. So if this is getting very, very large, this is tending towards 0. Plus e to the 0 we know is 1. So our area under the curve from 0 to infinity has a value of 1. So if you look at that, this is the actual curve that we were just talking about there. Okay, that is the curve of that. And you're going to see what I'm going to do is I'm going to bring in something here from our textbook. There you go. It's a dynamic figure here. And if you look, as that value of x, or the value of r, that r, is going out to infinity, you can see it approaches 1, eventually goes to 1 as we go to infinity. I think that's kind of cool. So there is our first example of an improper integral. What is the definition of an improper integral? Well, here it is. Fix a number a and assume that f of x is integrable over a to b, for b being greater than a. The improper integral of f of x from a to infinity is defined by the following limit if it exists. So from a to infinity, that following limit. So we have to set it up as a limit. We say that the improper integral converges. That's an important, we're going to see this over and over again, this idea of convergence over the next couple of units, if the limit exists, and diverges if the limit does not exist. Okay? So let's go back to our very beginning, or look at our objective. Students will use, what are we going to use? You got it, limits, in order to evaluate those proper integrals. That's what we're going to need to do. Okay, so there's a little introduction to improper integrals. Let's see, do we have another one? There you go. We have another problem there that we can look at. And see if you can set it up yourself from what we just talked about. Set up that problem and see. Well, if you did it correctly, you would have a limit, right? Set up as a limit as r goes to infinity, 2 to r, 1 over x cubed dx. And we want to show that it converges. That means we want to make sure that the limit exists. So go ahead, take a moment, and do that. Pause the video if you need to. Kind of see what's kind of going on. Hopefully, you've had an opportunity to do this by now. And when we get this, we're going to see that integral, right? This is x to the negative third. We add 1, divide by the new exponent. Hopefully you're ahead of me now in finishing this problem up. And what are you getting as your final answer? Well, if you see as this goes to infinity, this whole thing is going to do what? Yep, 10 to 0, go to 0. We're left with 1/8 as that area. Again, if you look at the figure, oops, wrong one. If you were to graph that, you would see it looks something like this. And we'll say here is 2, and we're finding the area from 2 to infinity. Okay, so here's just a little introduction. I'm going to leave you with one more problem to kind of think about before coming into class. You see this, we have our infinity, or negative infinity actually as the lower endpoint. So we have a picture here. And what I would like you to do is come to class prepared with this all set up and maybe even solve for this to go. Okay? So I hope you enjoyed this little intro on improper integrals, and come prepared to class to do more with improper integrals. Johnstone out.